Let's think about the infinite series. So we're going to go from n equals 1 to infinity of 1 over 2 to the n plus n. And what I want to do is see if we can prove whether this thing converges or diverges. And as you can imagine, based on the context of where this video shows up on Khan Academy, that maybe we will do it using the comparison test. And at any point, if you feel like you can kind of take this to the finish line, feel free to pause the video and do so. So in order to kind of figure out or get a sense for this series right over here, it never hurts to kind of expand it out a little bit. So let's do that. So this would be equal to, when n equals 1, this is going to be 1 over 2 to the 1 plus 1. So it's going to be 1 over 2 plus 1. It's going to be 1/3. Plus, that's n equals 1. When n equals 2, it's going to be 1 over 2 squared, which is 4, plus 2, plus 1 over 6, plus, let's see, when we go to 3, n equals 1, n equals 2, n equals 3, it's going to be 1 over 2 to the 3rd, which is 8, plus 3 is 11. So 1 over 11, maybe I'll do one more term. 2 to the 4th power is going to be 16, plus 4 is 20, plus 1 over 20, and obviously we just keep going on and on and on. So in order to use, it feels like this thing could converge. All of our terms are positive, but they're getting smaller and smaller quite fast. And if we really look at the behavior of the terms as n gets larger and larger, we see that the 2 to the n in the denominator will grow much, much faster than the n will. So this will start to behave, this kind of behaves like 1 over 2 to the n, which is a clue of something that we might be able to use for the comparison test. So let me just write that down. So we have 1 over, so the infinite series from n equals 1 to infinity of 1 over 2 to the n. And so when n equals 1, this is going to be equal to 1/2. When n is equal to 2, this is going to be equal to 1/4. When n is equal to 3, this is equal to 1/8. When n is equal to 4, this is equal to 1/16, and go on and on and on and on. And what's interesting about this is we recognize that this is a geometric series. So let me be clear. This thing right over here, that is the same thing as the sum from n equals 1 to infinity of 1/2 to the n power. Just writing it in a different way. And since the absolute value of 1/2, which is just 1/2, so because the absolute value of 1/2 is less than 1, we know that this geometric series converges. We know that it converges. And actually, we even have formulas for finding the exact sum of, or to find this, figure out what it converges to. And so we know this thing converges. And we see that actually these two series combined meet all of the constraints we need for the comparison test. So let's go back to what we wrote about the comparison test. So the comparison test, we have two series. All of their terms are greater than or equal to 0. All of these terms are greater than or equal to 0. And then for the corresponding terms in one series, all of them are going to be less than or equal to the corresponding terms in the next one. And so if we look over here, we could consider this one, the magenta series. This is kind of our infinite series of dealing with a sub n. And that this right over here is, well, I already did it in blue. This is kind of the blue series. And notice all their terms are non-negative. And the corresponding terms, 1/2 is greater than 1/3. 1/4 is greater than 1/6. 1/8 is greater than 1/11. 1 over 2 to the n is always going to be greater than 1 over 2 to the n plus n for the n's that we care about here. And since we know that this converges, since we know that the larger one converges, it's a geometric series where the common ratio, the absolute value of the common ratio is less than 1. Since we know that the larger series converges, therefore the smaller series, or the one that's where every corresponding term is less than the one in the blue one, that one must also converge. So by the comparison test, the series in question must also converge.